Okay, welcome students to the e-learning lectures on digital techniques or digital electronics. This is our fifth lecture. Let us revise what we have seen in last lecture with this format, most important lessons yesterday. Okay, so we have discussed about decimal number system, their representation, binary number systems, their representation, and representation using the base. So decimal number system has a base 10 and numbers are represented as 10 raised to 0 with the coefficients of given number 10 raised to 1, 10 raised to 2, 10 raised to 3. Okay, and in the binary number system it is represented as 2 raised to 0, 2 raised to 1, 2 raised to 2, right? We also seen few definitions, that is MSD and MSB, most significant digit, most significant bit, or a least significant digit, or least significant bit. Okay, then we have seen a few definitions regarding the binary number system, bits, bytes, and I have also asked you to see what do you mean by 1 KB, or how many bits are there in this 1 KB. So again, we'll go in more detail about this 1 KB, 1 TB, 1 MB. Okay, so this is what we have discussed in the last lecture. Bit, the smallest unit of the data, then nibble, that is a combination of 4 bits, right? So it starts from here, as in the case of array, so d0, d1, d2, d3, right? Then byte, which is a combination of 8 binary bits, so this is the 1 byte. Okay, it starts from d0 to d7, and then we have seen this word, combination of 16 bits, okay, which means 2 bytes or 4 nibbles in the double word. Okay, now let us get more detail about this. So I was talking about this pyramid. So at the very top we have bit, that is either 0 or 1, then nibble, which is a combination of 4 bits, then byte, which is 8 bits, and then this goes on increasing. Now you can see 1 KB, so this is 1 KB. Okay, then the 1 MB is equal to 1 KB. Sorry, 1 MB is equal to 1024 KB, right? 1 GB is equal to 1024 MB. Okay, and then we have this terabyte, gigabyte, petabyte, zettabyte, right? Okay, so this is what 1 byte means 8 bits, right? So we are talking about this 1 KB. How many bits we have in 1 KB of data? So 1 KB means 1024 byte. So capital B always represents byte. You have to remember this. Capital B always represents byte. Capital K always represents this kilo. Okay. Now here kilo is 1024. I will be discussing this how 1024 is considered, right? And then this capital M is represented as mega. Capital G is represented as giga. And nowadays we see our hard disk of computer systems are in TBs, 1 TBs, right? So capital T represents terabyte. Okay, so we are discussing about this 1 KB. So 1 KB means 1024 byte. Okay, now 1024 stands for kilo and B stands for byte. So 1 byte means 8 bits, right? Now if you multiply this 1024 into 8, since we are talking about here byte, so 1 byte is 8 bits, and when we multiply this we get this 8192 bits. So 1 KB of data means these many bits are there, 8192 bits, which are approximately 8 KB. So simply 1k into 8 is 8k, right? But in digital system, 8kb corresponds to these many bytes, 8192 bits. Sorry, it's a bits. Okay. Now, you might be wondering, like generally 1000 means 1 kilo. Okay, in our general this maths we can say, or general day-to-day life, when we want something of 1 kilo, so that then it is 1000, right? But for decimal number system, you have to remember this 1 kilo is equal to 1024. Okay, 2 kilo means the double of this, 2048, right? We don't have 3 kilo here, 3k. We can have 4k, so it is 4096, and so on. Okay, now this is perfectly logical. As I have in the earlier lecture discussed, that this subject is logical. Everything has a logic here. Now, what is the logic of having this 1024? So let us see. Now, since this is binary, we are talking about binary number system. Okay, so the base is 2. Now, if we go on finding the value of 2 raised to 0, 2 raised to 1, 2 raised to 2, so on, then at some point this value will correspond to some power of 2 raised to. Okay, this is about I'm talking. It's absolutely logical. Now, how? It's because of the base raised to the power. Now, what is the base of binary? It is 2, right? So 2 raised to 0 is 1. So we have discussed this. Anything raised to 0 is 1, right? Then 2 raised to 1 is 2. Okay. Then 2 raised to 2 is 2. So 2 square is 4. Sorry. 2 square is 4. Then 2 raised to 3 is 8. Now here everyone need to have this engineering calculators with you. For this first chapter we will be required this calculators. Okay. Then as we go on increasing this raised to power, then 2 raised to 4 is 16, 2 raised to 5 is 32, then 2 raised to 6 is 64, right? 128, 256, 512. Now 512 double is 1024. So 2 raised to 10, if you see in the calculator, then it is 1024. Okay, so as we have seen, binary number systems are represented in the uh, base raised to the power. So as we go on increasing the value of this power, we get this value, which is near to 1000. Okay, no other value you will find which is near to 1000. That is why in general we consider 1000 as 1 kilo, and for decimal number system 1 kilo means 1024. Okay, then as you go on increasing the this power, so 2 raised to 11 should be double of this, right? 2 raised to 12, so it is 2 raised to 12. Okay, so if you put in this value in your calculator, then that is what you're getting, 4096, which is equal to 4k. Okay, so this is very important point for this binary number system. And then this is how this 1 MB, 1 GB, 1 TB, they are represented. Now you can see here. So 1 KB means 1024 bytes, right? 1 MB, 1 MB means 1024 KB. So K is already taken here, KB is already taken here, right? So it is 1024 into 1024 into 8. Okay, 1024 into 1024 into 8. So that many bytes, sorry, that many bits, because we have multiplied this with 8, are there in 1 MB of data. So if you have a calculator with you, just check that it should be 8388608. So these many bits are there in 1 MB of data. Same is the case for this GB. Now 1 GB corresponds to 1024 MB. Okay, so again that 8388608 can be multiplied by 1024. So I even cannot read that number. The number is such long. So that many bytes are available. Sorry, that many bits. Again, we have multiplied that with 8. So that many bits are available in 1 GB of data, and then 1 TB. Okay, so this goes on. Okay, yeah. So this is what I am talking about. So byte means, now here you can see everything is in small case. So that is why this is taken in small case. Okay. So byte means B, which is 8 bits, means 1 byte, right? 1 KB means 1024 bytes. Okay. 1 MB means 1024 KB. 1 GB means 1024 MB. And you can see how these bytes goes on increasing. Okay, now this is represented in the form of byte. If we just multiply this with 8, since 1 byte is equal to 8 bits, then again you will find a big number. Now that big number indicates number of bits in each of this. Okay, you need to practice or understand this because this is very important. Okay, so this is about binary number system. Now let us see for this octal number system. Now as far as this digital systems are concerned, we hardly use this octal number system, but we have this conversion of octal into other number systems. So let us see again the representation or some details about this octal number system. So as in the case we have seen for decimal and binary, here since the base of octal is 8, the weights are expressed in the power of 8, right? So 8 raised to 0, 8 raised to 1, 8 raised to 2, 8 raised to 3, and so on. Okay, from uh, left side of this decimal point, and for right side of the decimal point, it is 8 raised to minus 1, 8 raised to minus 2, 8 raised to minus 3, 8 raised to minus 4, and so on, right? So for example, this. Now here one thing you have to precisely note that octal number system, since the base is 8, their symbol starts from 0 to 7. They don't have these numbers 8, 9, 10 or ABCD. They don't have, because their symbols are these only 0 to 7. So any number having if you see that octal number has this number, so then that number is not an octal number. That is what I want to say. Okay, so if this is a number 5642, now this is in the octal form, right? So this 2 into 8 raised to 0 plus 4 into 8 raised to 1 plus 6 into 8 raised to 2 plus 5 into 8 raised to 3. Okay, and then again 8 raised to 0 or any number raised to 0 is equal to 1, which is applicable for this 8 raised to 0 also. So here also we have, since these are digits, okay, so this is a octal digit. So this 2 is LSD and 5 is MSD, right? So you can try this number. Okay, oh, sorry, I have given here decimal. So this is octal number. You can try to represent this octal number in this format, and then you can post this in the comment so that I can understand that you have solved or you have at least try to solve this. Okay, now very important, hexadecimal number are very important because most of the time we will be dealing with these numbers. It's not only about this digital systems here, but in your computer architecture, mostly this hexadecimal number system is used because it has the base is 16, right? So it has 16 different symbols or different digits, which increases its uh, capacity. Okay, so 2 raised to 16, which is 65536. So these many different combinations can be taken with help of this hexadecimal number system. Okay, that is why it is very important, right? Particularly useful for human communications with computer. So that is what I was discussing. Then little difficult to interpret. Okay, because somewhere you have this A, then B, then C, all these alphabets, alphanumeric. This is alphanumeric. So you need to by heart this A equal to 10, B equal to 11. Okay, so let's see. Uh, little difficult to interpret is my interpretation. Okay, let's see if these concepts are clear for you. That would be easy for you. Okay, so here weights are expressed in the power of 16. So this is how. So 16 raised to 0, 16 raised to 1, 16 square, 16 cube, 16 raised to 4. Okay, as we move on to the left side of this decimal point, and 16 raised to 1, 16 raised to minus 1, 16 raised to minus 2, 16 raised to minus 3, as we move on to the right side of this decimal point. Okay, so here also MSD and LSD. So most significant digit and least significant digit. Okay, here we have to see the relation between decimal, binary and hexadecimal number systems. Okay, now as this is the last number system, now here we can see a relation between every number system. Okay, so a table is given here. Okay, now you can see this is decimal 0, right? Hexadecimal 0, and they are represented in this form, binary. So it is 0 0 0 0. Okay, then a decimal 1 is represented in a decimal 1. hexadecimal 1, right, whose binary equivalent. Now here we term that as equivalent because this number in decimal is 1, which is equal to 0001 in binary. They are equal, they have equivalence. Okay, then 2 in the decimal, 2 in hexadecimal, okay, corresponds to 0010 in binary, right? Now I have already discussed that if you see up to this point, then these numbers are same for decimal and for hexadecimal, and we already discussed that bracket and the base here corresponds to that number system, right? So if I say 2 here and if I say 10, then this becomes decimal number system. Okay, if I say 2 here and I say 16, now this becomes hexadecimal number system. Okay, so you can see 9 in decimal or 9 in hexadecimal corresponds to 1001. Now here it is different. 10 in decimal number system as A is its equivalent in hexadecimal number system, and it has binary as 1010. Now in the upcoming concepts or upcoming lectures, you will clearly understand how these binary numbers are generated, and at one point, without looking into a book or in this slide, you can write down this complete table. Okay, then B corresponds to 1011. Okay, I mean this is the equivalence. Here we haven't considered octal number system because I said very often we use this octal number system. What we are very much concerned is about decimal, hexadecimal, and binary. This is because binary number system, computer understands binary number system. Computer architecture mostly deals with hexadecimal number system, and we as of now have uh, discussed or we know this decimal number system. Okay, right. So in upcoming lectures, we'll try to understand very deeply and try to fill this table once again. Now you can try this. So this is 3FD. Okay, now this base is 16, or without having this base you can understand that this is a hexadecimal number system since FD is mentioned here. So this number can be represented in that D into 16 raised to 1. Sorry, here it is 0, right? Then F into 16 raised to 1. Okay, and 3 into 16 raised to 2. So this is 16 raised to 0, 16 raised to 1, 16 square. Okay, then this is 16. Now D corresponds to 13. You can see here D corresponds to 13. So while calculating, we are supposed to convert these to decimal number system. So 13. Then F corresponds to 15. So here F is replaced by 15, and then it is multiplied. 16 raised to 0 is 1, 16 raised to 1 is 16, and 16 square is 256. Okay, and then this number turns out to be this. Okay, so 3FD has equivalent number 1021 in the decimal. Okay, this is concept of conversion, which we are going to look into upcoming lectures, right? One more another example for you, so you can try on this, trying to represent this number in this format. Here 2 a, now you can see a is represented as 10, then 3 d is represented as 13. Okay, then a is again represented as 10 and 1 is a 1. Okay, so now here we have given this decimal point. So as we move on to the right side, so it is 16 raised to minus 1, 16 raised to minus 2. This way you can try to represent this number, right? So I hope this octal hexadecimal numbers are clear for you, and you could relate the difference or equivalence between this decimal, hexadecimal or binary number system. If you still have any doubt, you can post your doubts in the comment box, or you have my WhatsApp number. You can simply anytime ping me for the doubts related to this. Okay, yeah, number system. Now as we have discussed about all the number systems, now let us move ahead and see number system convergence. Now why this is required? We already discussed this, that we understand a certain language. Okay, computer understands some different language. It's simply like uh, if I am a Marathi, my mother tongue is Marathi, and if I want to understand other state language like Kannada or Telugu, right? So there need to be in between something where communication can take place. Okay, so similarly, now we understand decimal and computer understands binary. Okay, so as to represent the data in the memory, we have hexadecimal number system, right? So we also, as a engineer, should know this conversion, that how certain number is represented in binary and how a binary number can be converted to decimal or hexadecimal. Okay, now I said this, or you have 2 or 4 marks question based on this conversion. Okay, if you look in the question paper, we'll in one of the lectures we'll try to cover what different questions are covered in the question paper also. Okay, now you all need to have your engineering calculators. I already discussed this. This is very important. How many conversions are we supposed to study? Okay, so we have 12 different conversions. Considering each number system has 3 different conversions. We have 4 number systems and 4 3s are 12. Okay, so consider decimal number system, decimal to binary, decimal to octal, decimal to hexadecimal. Consider binary number system, binary to decimal, binary to octal, binary to hexadecimal. Consider octal number system, then we have octal to binary, octal to decimal, octal to hexadecimal, and then hexadecimal to binary, decimal, octal. So each number system being converted to each other number system. Okay, so in the upcoming lectures we are going to see the conversion in detail. For that purpose you need to have calculators ready with you, and you can even by heart the multiplication table here of corresponding base. So uh, 2 2 multiplication table you already know, then 8, 10 and 16. So these multiplication tables are really going to help you to convert this or understand this conversion. Okay, so you can take that as an assignment, and then we'll see in next lectures that convergence in detail. So we'll start with this decimal number system, how a decimal number system is converted to binary. Okay, so that's all for this lecture. Thank you. Stay safe, stay healthy, and again have a happy e-learning.